Okay, now we will consider the solutions to linear time invariant system. Consider the state space description of a linear time invariant system expressed as these two equations, and where the x dot t, xt is the state, and ut is the input, yt is the output, and the input trajectory u as a function of time. The state solution is a function of time as well, and we will find we will here we emphasize the initial condition will be x naught t naught. Then we will ask two questions. Do there always exist solutions of linear time invariant for every initial conditions, or there exists a solution that is unique? So this is the existence and uniqueness question. To address this question, we will focus on more abstract description. Now, the dynamic equations is governed by x dot t equals a function of the state and input and the time. And initial conditions, x t naught is x naught, and the x dot is that's what we said. And notice that we need to check both initial conditions and dynamic equations. Encoded by F, this is our dynamic equations, constitute a state solution. Okay, let's see an example. No solutions for initial conditions. So here we have a sign. So that is -1 and 1 when x equals bigger than 0 and when x is smaller than 0. Consider a solution that x naught t naught is 0, and the system starts from t equals naught, and x naught equals -1. And by time t, the x becomes infinitesimally negative, and x dot becomes positive. If x dot is positive, bring it back to 0 state. However, a candidate solution satisfies the initial condition leads to x dot equals 0. This is different from x dot t equals -1. So in fact, the system performing an infinite number of transitions in 0 time. Okay, so example 3 will have infinite number of solutions. So consider ODE given by this equation and the initial conditions 0, 0. For A is bigger or equal to 0, we will have this candidate solution. And notice that when A is bigger than t naught equals 0, the initial condition x naught equals naught is always satisfied. When t is smaller than a, xt equals naught is a trivial solution of the ODE. Trivial solution, notice this. And consider how the case where t is greater than a, we will always get xt equals this, no matter for what t we choose. So, it's not t, so no matter, as long as t is greater than a, so there will be an infinite number of solutions exist. So the first example highlights the necessity of f to depend continuously on xt, and the second one shows that continuity is not sufficient, as the function tends to have infinite slope as xt equals 0. So we come to our first theorem, existence and uniqueness solution. Let x dot becomes this, and assume that the input and the f are continuous functions with respect to time. F is called the Lipschitz continuous with respect to first argument xt. Notice that u being a continuous function of t is rarely the case in practice. And there always be a discontinuity point may exist, and we will use a piecewise continuous function, not necessarily strictly continuous. The only difference is that the unique solution should satisfy this. And we will further two assumptions. Within every finite time interval, the number of discontinuity is infinite, and the left and right limits at the discontinuity is well defined. So here we will assume the input trajectory is well behaved. And theorem 2, we have the linear time invariant to a set of equations admits a unique solution, x state and the output y. So to prove that, we will admit a unique continuous state suffice to invoke theorem 1, existence and uniqueness theorem. Then we will show that the function f will be ax and bu. This is the Lipschitz continuous with respect to xt. But the Lipschitz continuity definition considering two different states. We will have so two different states, we just use another symbol x hat. So the difference, so this is the norm, the Euclidean norm between these two states. We will have this. And we will prove that in the appendix, so we don't need to worry about here. So by a positive definition of semi-definite matrix implies that this form will be smaller or equal to with lambda, that is the singular, this is the eigenvalue, and this equation represents the maximum single value of A. So overall, we will have shown that this equation, taking square root of both sides. So this implies that xt bit u is a Lipschitz continuous with respect to t, and the L, we mentioned that the maximum singular value of A will become the Lipschitz constant. And the fact that the output solution y is unique and continuous follows directly from the fact that the output equation is a linear function of x. Hence, a unique continuous state solution implies a unique continuous output. Characterization of solutions. So theorem 2 shows that a linear time invariant admits a unique continuous state and output solution. Here we provide a closed form characterization using our initial conditions and let the t naught become 0 for simplicity. So in particular, the state and output solutions are given by 0 input transition. We denote it as phi, and the 0 state transition. And this is for the state. And the output will be 0's input response and 0 state response. So notice the expression of the equation. This is a convolutional integral. So here phi is called state transition matrix. What is a zero impulse transition? This is state solution if the system is autonomous. If ut is 0 for all t, that is the definition of autonomous. And this is a linear function of the initial state, x naught. And also satisfy the term state transition matrix for phi t. So phi t x naught takes a state at time t. Zero state transition. This is convolutional integral, and it is a linear function of the input ut. To see this, consider the superposition principle of linearity, and we will find that this equals this. This is the superposition principle, and this was anticipated as integrand is a linear function of u, and the integral is continuous analog of summation. So next, similar comments pertain to the output solution YT, which is the response, which comprises two terms, zero state, zero input response, and zero state response. So the transition matrix is phi, which is represented in a matrix exponential and expanded by a Taylor series. So it satisfies the following properties. Four properties. First is phi 0 equals I. So when t is 0, only I exists. And differentiate, we will have a plus, that will become 2a t So we have get the second property. And the third is invertible, and its inverse is phi minus t. And when the inverse and the non-inverse times together, we'll get the identity matrix. And the fourth is phi t1 plus t2 equals phi t1 times phi t2. And note calculating integral or the derivatives of matrix involves calculating the integral of every entry matrix involved. And the x80 is not equal to a matrix where each of the entries is raised to exponent. So for arbitrary matrices A and B, only if A, B, and BA commute, then we can make this unequal become equal here. We already shows that the convolutional integral and the phi delta x0 is indeed the unique state solution of this linear time invariant system. The YT star is the output solution following the YT equals CT plus DUT. To prove that XT is a state solution, so we have quite a lot left in lecture 2, so I will stop it here today.